Welcome everyone to the webinar. Thank you for joining. Our topic today is FPGA accelerator cards, and specifically the new VectorPath S7t-VG6. I'm Marcus Weddle with Bittware. During the main presentation, if you think of a question, please ask it in the questions control panel. We have staff online that can answer you in chat during the presentation. Of course, you can also wait until the Q&A session at the end, where we will answer your questions live with our presenters. So let's get started. Our first presenter is Steve Menser, VP Sales and Marketing for Achronix. Steve has 25 years in the FPGA industry, and you can see a range of positions he held at Altera, which of course is now part of Intel. Steve will be joined by Craig Petrie, VP Marketing for Bittware. Also with decades of experience in FPGAs, Craig began at Nalatech, which most of you probably know was merged with the Bittware brand in 2018. All right, I'm going to turn it over now to Steve to lead us into the main presentation, and I'll be back afterwards for the live Q&A.
Thank you, Marcus. We're excited to be able to have this opportunity to talk at this webinar about the recent announcement for the VectorPath S7t-VG6 Accelerator card. We'll go through some of the details of the card and then allow for questions at the end. First, an introduction to make sure you know both companies that are working on this product together. Achronix, we are a company that focuses on high-end FPGA and best-in-class tools to support the FPGAs. We are unique in that we are the only FPGA company that focuses on high-end standalone FPGA products, as well as selling embedded FPGA IP technology that can be integrated into ASICs or SoCs. We're focusing on our latest product family called Speedster 7T. It's a product family focused on high bandwidth and AI applications.
Thanks, Steve, and hi, everybody. This is Craig Petrie from Bittware here. For those of you who are unfamiliar with Bittware, we are part of the Molex group of companies, and we focus on FPGA-based acceleration for applications including compute, network, storage, and sensor processing. These programmable FPGA products increase application performance and energy efficiency whilst reducing total cost of ownership for our customers. At Bittware, we have a 30-year track record of successfully designing and deploying advanced FPGA accelerator products. As part of the Molex group of companies, we are the only FPGA card supplier of critical mass able to address enterprise-class qualification, validation, lifecycle, and support requirements. The collaboration with Achronix is very exciting for Bittware, and together we feel that we're greater than the sum of our parts.
Before we get into the details of the card, we want to talk about a little bit of the background. So there are many forecasts out that predict hardware accelerators, so silicon-based hardware accelerators are going to be in excess of $20 billion by as soon as 2023. And the fundamental reason for that is that your traditional methodology of using an array of servers based on Xeon processors cannot address certain workload problems sufficiently for the performance requirements or the energy requirements needed. So I'm going to go into a little bit of detail about that. If we break up application segments into compute, networking, storage, and sensor processing, what we've shown at the bottom are all of the, or many of the various workloads that have to be done on data. So historically, data would ultimately have to be moved from point A to point B. Now we're in a domain where there's work that has to be done on that data before it's moved. So some simple examples are compression and encryption. And some other examples, of course, are a very fast-growing market segment in AI/ML. In fact, you'll see at the bottom here, we've highlighted and noted the different workloads that are AI/ML oriented. What you'll see, though, is across this large array of workloads is that it's very difficult to create one technology that will address all of these different workloads as a hardened function or as an ASIC function. Ultimately, if there were a way to do that, there would be ASICs or chipsets that would solve this problem. But again, from a CPU perspective, there's inefficiencies. And so we see that either GPUs or FPGAs are programmable solutions. And one of the benefits of FPGAs in particular is that they have the ability to create orders of magnitude acceleration and they can address all of these different workload types.
The purpose of this slide is to highlight the trends we see in the marketplace and, together with Achronix, explain how we're helping to address them. Over the course of the last 5 to 10 years, we have seen the success of GPGPU technology from NVIDIA. This has changed attitudes and generated an acceptance of acceleration technology as a means of increasing application performance. More and more customers are using heterogeneous architectures, which provide a mix of different technologies, each with their own pros and cons, and when used in concert, these platforms provide an overall benefit for a spectrum of applications. As GPGPUs deliver diminishing returns, customers are now looking for where the next wave of performance improvements and energy efficiencies will come from. There have been some high-profile FPGA success stories in the market over the last 3 years. Examples include the Microsoft Catapult program, which used the Altera, now Intel, ARIA 10 FPGAs to accelerate the Bing search engine. Microsoft has continued to invest in applications using FPGAs and now use the Intel Stratix 10 FPGA for their Brainwave program, which runs a persistent AI neural network. Most recently, Amazon's AWS F1 cloud instance has been augmented with Xilinx UltraScale Plus FPGAs. These are all good examples of what we call chip-down designs, where hyperscale customers invest significant time, money, and people resources to create a special implementation to solve 1 or 2 application requirements. What we see is that as the FPGA rides the classic technology adoption curve, the consumption model changes. Tier 2 hyperscale and enterprise class customers have a different set, a very broad set of application problems to solve, and can't justify the investment of a chip-down model. They want to purchase off-the-shelf products at the card and the server level. This is why we now see server vendors such as Dell, HPE, and IBM selling FPGA cards in some of their popular server platforms. The 2 main FPGA vendors, Intel and Xilinx, have also recognized this market trend and have launched their own range of FPGA PCIe accelerator cards, the PAC and Alveo range respectively. In the next few slides, we will explain how the S7t card and design tools will help address some of the detailed technical requirements we see from our target customers. We're also trying to ensure that we are addressing many of the business requirements that our customers experience. They're under significant pressure to improve energy efficiency in order to reduce total cost of ownership. The reconfigurable nature of the Achronix Speedster 7t FPGA allows our customers to achieve ASIC-like performance whilst reacting quickly to new application requirements. The fact that we are able to deliver the Achronix S7t FPGA as an enterprise class off-the-shelf PCIe card or server platform helps our customers prove out their application, then ramp quickly and cost effectively. The hardware they use for their proof of concept is also their production-ready hardware, ready to scale. All of these factors together improve time to market and reduce risk.
Okay, so now we're going to go into the details of the VectorPath Accelerator card. First, in terms of the card form factor, this is a full height card that's double width. This is the same form factor as GPU-sized cards. Very importantly, there are multiple cooling options, passive, active, as well as liquid. And this is built to be enterprise class in terms of its overall quality.
So our goal in this collaboration is to deliver enterprise class products. And that obviously means quality hardware, but also means design tools and utilities. The bundle which we're providing with Achronix includes the hardware, but also includes the Achronix ACE design tools and a toolkit from Bittware. The toolkit leverages 30 years of FPGA card experience and features. The headlines for the toolkit include a sophisticated boards management controller, or BMC, that allows customers to monitor the health of the card under application load. For example, power consumption, voltage, current, and temperature monitoring, plus various other parameters that are important to the customer. The toolkit is supported with the latest versions of Linux, most of which our customers use. But for some customers who have legacy application complications, we also support Windows as an optional extra. There is an extensive API and PCIe driver set available, multiple application example designs demonstrating how to move data between each of the main FPGA peripherals, PCI Express, memory, and network ports. These are delivered with source code. Finally, there's a diagnostic self-test, which is the baseline of our technical support and warranty services. This test is part of our production test regime and is used by our customers before starting their application to ensure that the card has survived transport, handling, and installation. It is a golden image useful for debug, which verifies that all features are working to maximum performance. The purpose of this slide is to summarize the headline features of the Speedster 7t FPGA Accelerator card. We tried to make sure that the Speedster 7t device features and IP are exposed to customers at a card and a server level. First up is the PCI Express connection, which is the full 16 lanes. The card will initially support PCI Express Gen 3, which is where the market is today. However, the card has also been designed to support Gen 4. Our goal is to qualify Gen 4 and upgrade the product specification over time. We're very lucky in that the Achronix Speedster 7t FPGA has hard IP supporting 16-lane PCI Express Gen 5. When the time is right, we'll look at the signal integrity of the card and make any necessary tweaks to ensure compatibility. The Speedster 7t FPGA is rich with an array of multi-line rate SerDeses, MACs, and FEC IP supporting everything from 1 to 400 gigabits per second. We have leveraged technology from Bittware's parent company, Molex, to design in two types of network cages, QSFP56 and QSFP-DD, which means double density. The QSFP56 is the 1 by 200 gigabit E port. The QSFP-DD is the 1 by 400 gigabit Ethernet port. Both network ports can be broken down into multiples of 10, 25, 40, and 50 gigabit E connections through use of breakout cables from Molex. The other headline features of the Accelerator card include the innovative memory architecture. Instead of using expensive HBM2 integrated memories on their FPGA, Achronix has included GDDR6 hard IP. The Bittware card supports 8 independent banks with a capacity of 8 gigabytes. This produces 4 terabits per second of external memory bandwidth, which is in line with the performance achieved using HBM2, but without the cost. GDDR6 memories are used extensively on GPUs and are multi-source. This architecture allows Bittware to customize the card for volume applications. A customer might say, look, I'm only using half the memory banks for my application. Can we depopulate 4 of the banks in order to reduce price and power consumption? This is a straightforward option that would require a different FPGA and potentially a new PCB if we're using an HBM2 enabled device. In this case, we can simply depopulate, reduce cost, and save money for the customer. We've also included a single bank of DDR4 as a buffer and cache level memory option for customers who need that level of application buffering. This slide summarizes some of the more subtle but hugely important features needed for applications to run efficiently. Bittware has poured all 30 years of experience to ensure that this product can cope with the varied requirements of compute, network, storage, and sensor processing workloads all in one card. You won't see many of these features on other FPGA cards in the market. First up are the SMA connectors on the front panel to the left-hand side. These are clock inputs, including 1 PPS and 10 megahertz, which allow customers to synchronize multiple cards for timing critical applications. Without these, it is extremely difficult for customers to scale network-enabled applications. At the right side of the card, we have a general purpose digital I/O header. This is a relatively low-tech connector running 8 single-ended pins from the Speedster 7t FPGA through voltage buffers to convert from 1.2 to 3.3 volts. This header is extremely important when customers are integrating new acceleration technologies into legacy systems which need simple digital triggers or control loops. The final card feature we want to walk you through today in detail is an expansion port using the industry standard Occulink Edge connector. Occulink stands for Optical Copper Link and is a PCI Express interconnect system. There are 4 main use cases for this port on the S7t Accelerator card. The first allows the FPGA to interface directly with the NVMe flash arrays. This allows data captured through the network ports to be pre-processed, then saved directly to NVMe storage or retrieved by the FPGA and processed as part of a database acceleration or big data application. The other use case we see at Bittware is the need to scale FPGA applications across multiple devices. As good as PCIe is, when you try to scale via the host interface, chipset, and driver and operating system, you inevitably will kill performance and increase system-level jitter. Using the application expansion port as a simple SerDes, i.e. non-PCIe protocol, customers can interconnect Speedster 7t devices directly through a simple cable assembly that can be provided by Molex. Customers can interconnect using whatever topology best suits their application, daisy chain, ring, mesh topologies. Using this technique, customers will have a low latency, high bandwidth, and most importantly of all, a deterministic interface between FPGAs in their system. The third use case is as an I/O rich as this card is, there are always some customers who want just a bit more in terms of network connectivity. In order to help cater for those customers, an adapter can be used to bring in even more network ports from the front panel into the Speedster 7t FPGA via the expansion port. And the last use case, as was the case with the GPIO header on previous slides, the Oculink expansion port, which is protocol agnostic, can be used to integrate new technology into older systems.
Now I'm going to talk about some of the features of the Speedster 7t device. So as we click forward here, I'll highlight the NoC, or network on chip, and it's a two-dimensional implementation. So you can see it highlighted here, and I'm not going to go into all the details of the NoC, but basically the NoC is very high bandwidth, so 512 gigabits per second for each horizontal and vertical column, as well as connectivity to the high-speed interfaces, which include the Ethernet, the PCI Express, the GDDR6 ports, as well as DDR4. There are multiple different modes for communicating to the NoC. The most common one is an AXI interface, which is very standard in terms of any design engineer understanding how the interface works. And where those points of connectivity are is any point where the horizontal rows and vertical columns cross over each other. There is a what we call a NAP, or a NoC access point. And so you can get either on the network on chip, or you can get off at any one of those points. And so it's a very powerful feature because it means that the NoC is distributed across the FPGA fabric for doing real-world implementations. So let me give you an example here. What I'm showing here is a cartoon of an FPGA with the desire to create two different accelerator functions, Accelerator 1 and Accelerator 2. And you can see the different GDDR6 ports. So if I wanted to connect to any of these ports, let's just say two of these ports, I have to build functionality to make that happen. Ultimately, as a user, I really only care about the accelerator functions. Everything else that I have to do is, because it's an FPGA, I have to design myself all the functionality for it to talk to the outside world. So if we click forward, you'll see the functionality that has to be done. So first of all, because I'm talking to GDDR6 ports, I have clocking from the outside world, and I need to synchronize that to the clocking inside the FPGA. So I'll go through a standard structure like a FIFO. That's fairly straightforward. What is more complex is because the different accelerators need to talk to both of the different memories, as there will be a shared memory space. There has to be a control mechanism, or really a switch function, that does the addressing, decode, and routing. There needs to be controls and back pressure to make sure that the two accelerators don't talk to the same memory location at the same time. And then all that has to be done in the reverse direction also. So if we click again, you'll see that the area that's highlighted in red here is really of no value, as I said earlier, to the customer, except obviously it allows the accelerator functions to talk to the outside world, so it has to be done. It's a necessary evil. There's a couple of challenges associated with this. One is, you can see at the bottom, we've highlighted that this area in red grows at a quadratic rate every time you add a new port to the switch function. So whether it's another memory port, or whether it's a high-speed interface, or another accelerator. So it grows at a very fast rate to the point where you will have much more of your circuitry that is this red functionality, in other words, the connectivity to the outside world, versus the functionality that you would otherwise want to focus on, which is your accelerators. Probably more importantly is that it makes the design and timing closure very difficult. In reality, when you are talking to very high performance interfaces, what will happen from a place and route point of view is the circuitry is going to try to be pulled towards the port of connectivity. And what that means is you're going to be stretching between your accelerator and the various different ports. So it becomes very difficult to close timing. What's different in Speedster 7T FPGAs is because we have this 2D NOC with these NOC access points, or NAPs, that are distributed across the FPGA fabric at every point where the horizontal or vertical columns intersect or cross over each other. This means all you have to do as an engineer is very simply design your accelerator RTL, whatever expertise you have, and simply do an AXI connection. So you would create an instantiation of a NAP, and you hook it up, and from there, the Achronix software tools called ACE would take care of all of the routing between your accelerators and the different memory ports, or different high-speed ports like Ethernet, PCI Express, etc. This is very important because the ecosystem will be something that is critical for this product, as there will be many different types of solutions built to create those workloads we talked about before in terms of different types of accelerators. Because this environment is so much easier for engineers to design with, it means the ecosystem will be able to thrive in the sense that the different ecosystem companies that have a specialty or a type of IP to offer, they will be able to essentially be able to create an end-to-end solution. And the way that works is the IP provider will simply create the functionality for whatever their value proposition is. Again, it could be encryption, acceleration, or any type of AI ML application. And all they'll have to do is instantiate a NAP, and then they'll be talking to the outside world. So we currently have a fairly decent-sized ecosystem. It is growing very quickly, and we expect it to continue to grow very rapidly because this is a very easy environment for both designers as well as ecosystems to build their IP for an end solution product. The other thing I wanted to talk about is inside the Speedster 7T device are MLPs, or machine learning processors. These are what would be traditionally called a DSP block in standard FPGAs, but they've been optimized specifically for AI ML applications. I'm not going to go through all the functional description of them, but I want to give you some of the highlights about them. So first of all, in terms of them being distributed throughout the device, you can get over 40,000 int8 MAC operations on this card, on this S7T card, and they'll run at 750 megahertz. That equates to over 80 tera operations per second functionality. And then another benchmark that's often cited is ResNet 50. And in that benchmark, this delivers 8,600 images per second. I do want to comment about GPUs, which have otherwise been focused on AI ML, mostly in the training area. One of the challenges of AI ML is that because they have many different engines with a cache structure and are largely designed similar to what you would have in terms of a sequential implementation on a CPU, you get into memory delivery challenges or data transfer challenges where the actual compute engines are really only being utilized about 10 to 20% of the time. So whereas you would hear a GPU quote, let's say 130 tera operations per second, in actual results, when you're measuring the images per second, for example, you get something closer to 15 to 20 tera operations per second. Whereas because of the Speedster 7T high bandwidth memory implemented as GDDR6, plus the network on chip, plus these highly optimized machine learning processor blocks, we're seeing that we can deliver up to 80% efficiency for AI ML implementations.
Okay, as mentioned earlier in the webinar, we explained that as FPGAs ride the technology adoption curve, we see the consumption model changing from chip-down design to card to integrated server platform. For customers who wish to purchase at the server level, the S7t card is available as part of Bittware's TeraBox range of products. Over the course of the last few years, Bittware has seen an increase in design wins and revenues from the TeraBox range, which we relaunched earlier this year. FPGA cards are delivered to customers as pre-integrated, pre-tested Dell or HPE systems with the mechanicals and the thermals already figured out, plus a comprehensive warranty covering both the server and the FPGA card. The operating system, Bittware Toolkit, and Achronix ACE design tools are all preloaded and ready to go. Customers just need to apply power, log in, and run the diagnostic test to verify that everything is good. The TeraBox product range was created to address two specific types of customer. The first is a developer who is trying to get their proof of concept ready for their customer deadline or the boss's demo. Time to market and minimizing setup and hassle are really important. So the TeraBox range allows the customer to place a single purchase order for a single line item and get everything delivered in one package. Once the proof of concept phase is complete, the next customer type we tend to meet during the deployment phase is a program manager or an IT lead. These customers are usually unfamiliar with the details of the FPGA technology and instead care a lot about application deployment and management. They want to understand service level agreements, warranties, technical support, utilities for monitoring product in the field, and upgrade and maintenance schedules. As part of the Molex group, Bittware has a global supply chain and infrastructure, which you can uniquely leverage. Furthermore, Bittware is also part of the Dell and HPE OEM programs. This means that customers, if they prefer, can purchase TeraBoxes directly from Dell or HPE under their current contracts.
So in terms of the availability, the VectorPath S7t board will be available in the beginning of the Q2 2020 timeframe. Its 1 unit list price is $7,500 US. But beforehand, folks can start their designs in terms of designing the FPGA functionality using the Achronix ACE design tools. These tools are available now, so folks can basically, as I said, they can start evaluating the software or preparing their designs for the card's availability. So let me just do a quick wrap up and then we'll transition to some questions. So first of all, it is a very high growth market. The idea of using accelerator cards was proven out in terms of GPUs, and we've seen that drive into data center applications, and it's obviously been valuable across many different application segments. Achronix and Bittware are working together. It's an exciting partnership in delivering some unique functionality. The card is powered by the Speedster 7T FPGAs, and we talked about the network on chip as well as the MLPs. And then Craig talked about some really interesting innovative features on the card that comes from Bittware's many years of experience delivering this technology. But ultimately, what this is, this collaboration and this solution, has been focused on trying to deliver a complete solution, enterprise class, that's a low-risk product that you can use for your production applications.